Okay, so let's get started, right? So let me turn back to this. Okay, good evening, everybody. How are you going? I think it's Friday night. It's very nice weekend coming. The haze has gone. I think you're already. It's a little bit embarrassment to play magics in this good Friday night. So I'm not going to show you many magic things, but just get a general idea of the machine manufacturing automation, especially the charter vibration. Last time, Professor Tegu already introduced the dynamic equations. How can you modeling the one mass spring damping system and two mass two spring two damping system, right? You remember that? So actually this lecture is based on that, but we are very focused on the charting vibration, and this is very key problem you need to solve when you want to build a very nice machine with high quality and accuracy. So before I'm going, just a very brief introduction. KMT, I'm actually a research fellow and supervised of Prof. Yimin Chen. He's in Taiwan for a conference. Before joining NTU, I was actually in industry for 3 years in international construction manufacturing company in Zhunan. We are doing truck mounted pump machines, different kind of products and basic research. I spent 3 years in University of Kasim. Actually, it's a very small town and a very small university near Rome. It's like 150 kilometers. You can travel train from there to Rome. It's a very fantastic city, different culture. I have to say it's nice to be there. I got my master's degree in Beihang, in Beijing. I think many students or PhDs did their study in Beijing also. My bachelor's is in automation, actually. So, but my research area actually is not in machining, but in robotics, especially in mechanism, and the industrial robots. So here is my email address. So if you have any questions or you want to visit our robotic research center, you can send me an email. We can do an appointment. I can show you around all different kinds of robots, because I think you are very interested in robotics. Prof. Chen already gave you a very nice lecture on different parts in kinematics, dynamics. But I think the most important way of learning is really you need to see and play with this kind of things. Then you get to experience how it works, right? Okay, so before we start the lecture, I'd like to show you a video. Actually, I don't know how many guys you have ever seen or programming on a CNC machine. I don't know, but this one, DMG Mori, actually we currently run a collaboration project with DMG Mori. It's the largest CNC machining manufacturer in Germany, internationally recognized. They're doing all kinds of top rated CNC machines. Actually, they have a sub company here in Singapore, and we are collaborating with them to develop some robot, a dual arm robot, to help them to loading and unloading these kind of work pieces. Because you know this machine expensively, they want the machine to run like 24 hours, 7 days. So in Europe or in Japan, the human labor is highly expensive, also in Singapore. So they want the robot to do it. Here you just show some very idea of how this machine looks like what kind of job it can do. I think when first time I saw this, I think this is really amazing. That in terms of the speed, accuracy, and now they make this kind of machine very complex. They have like 36 axes. They can automatically change the cutting tool, mining or cutting. Oh, and recently, if you're interested, they are using a kind of laser technology that is doing additive manufacturing. That in Singapore we have a very nice industry that is aerospace engine repairing. So let's say if you have an airplane, it's working in Singapore, but you want this parts to be, you want the airplane take off again in a very short time, but you're short of the components. The components manufactured in US or Europe takes several weeks to come. And this kind of machine, they can build this kind of complex components for the airplanes without wasting materials, because they're using this kind of laser-based additive manufacturing, and plus this CNC cutting and mining. Okay, so I recommend you to search on YouTube if you're interested, and you can get more knowledge about how it works, what's problem it will have. I think this is very important area for industrial, because it can make all kinds of components for automobile, aerospace, ships. Okay, so just quick introduction of this. So now we come to the vibration, the chart vibration. Actually, there are two kinds of vibration here we are talking about. First is the cutting force can be periodically in case of money. If you remember last lecture, Professor Tegu already introduced the machining structure. Actually, it's not a very rigid body. It can be molded as a single degree freedom damping spring system or multi-degree freedom mass damping system. So it has some vibration, and if you apply the cutting force on the workpiece, it will cause this kind of a periodically vibration. Of course, there are also other factors such as the non-symmetrical cutting edges of the workpiece, and have a run out of your cutting tool, or there's not balanced mass between of your workpiece or your cutting tool, and all these factors will be have an influence on the cutting force. So the problem is if any harmonic of this kind of periodical excitation force match the kind of natural frequency of the machine structure, as you already did in last lecture. There is a kind of structure frequency of the machine of this kind of mass damping system. So that if you have this kind of harmonic periodical force on it, then will be excessive vibration will be output result, and then that one will greatly influence your machine, your product quality. Okay, so there are different kind of ways that you can actually solve this problem, and from analytical solution way or from experimental test, you can determine actually the structure frequency, natural frequency of your machine structure. And you can use this kind of information and prevent this or reduce this kind of force vibration. Okay. The second kind of chart vibration we are talking about tonight is kind of self-excited vibration, and this also create a very great influence on the machine workpiece production quality. And here in this lecture, we'd like to show you what will this happen, how can we analysis, in a scientific way, or how can we prevent this happening on a real machine, right? Okay, so before also I want to show you this what will happen for this kind of child vibration. What is? So this is actually animation, shows a kind of a laser machine of also known cutting. As you can see with the time lapse, the kind of vibration between the workpiece and the cutting tool is becoming bigger and bigger, because this is because of the cutting force is harmonic with the natural frequency of this kind of machine structure. Okay, and this kind of things we need to prevent to happen. Otherwise, the manufactured workpiece is not good quality, right? So this is kind of self-regeneration of this kind of vibration because of this structure, natural frequency combined with the cutting force. Okay, here just show you two pictures of the effect of this chattering vibration on the surface. This one shows not the cutting, but the meaning, like 2 degrees freedom. Here you can see actually this is the machine, the surface that the chattering vibration happened. It shows this kind of uneven crunched surface. And here is a well machined workpiece without any chattering vibration. You can see it's very good quality. So let's take a look how this will happen. So there are actually the reason for a machine to exceed this kind of child vibration is in several steps. The first step, as you can see already in that animation video, the cutting process actually is, as I mentioned before, is a kind of periodical forces due to several reasons. This is the first kind of due to the unbalanced mass or this kind of running tool of the machine tools. And this kind of periodical machining force, if the harmonic interact with the machine structure frequency, like 2 or 3 or 4 times this harmonic natural frequency, then it will result a large vibration amplitude on the surface of this machined workpiece. And then this result in a very weird like surface pattern, like some parts of this workpiece is deeply manufactured, but other parts is not so machined. So when this spinner, because you are mounting the workpiece on a spindle, and when the workpiece turns around, then the next cutting edge will cut a material with different variable stiffness. Of course, these days when we show you later, if there is a phase shift, this kind of charting will be growing. But if there is no phase shift, this kind of vibration will keep in a certain area that the surface still smoothly. Okay, and then if there is a phase shift, there will be result excitation force that causes this chip thickness to increase exponentially. That is very bad, as you already see that in the video, the chip thickness. Because you want the machine to a certain cheaper thickness as you want it due to the feed velocity of your machine tools. But this one will cause this kind of increase of your chip thickness. So let's see how this it works. First, I'll show you this small animation. Okay, so this is actually animation of this kind of Osonogo, this kind of laser machine. It's very simple machine. You have your workpiece inside the trunk, and the trunk will spin the wheel revolute in a predefined velocity, and you have your machine tool here to machine this workpiece, and here the dimensions we say the A. So here actually we show you in different side view of this example. I will show, or will explain you two more details here, maybe. Okay. If you look at this picture, actually you're very familiar. Hope you remember what Professor Tegu told you to modeling one single mass damping and spring system. But this is very similar. It's based on his lecture. So actually you have, let's say this is the machine, CNC machine structure. We simply model it as one single degrees of freedom system with the mass, with the spring and the damping. So here you have the machining tool. You apply this kind of machining force on this workpiece. Okay, and then this workpiece is actuated by the spindle in a certain speed. So let's take a look how we do a calculation of this chattering and vibration. So, okay, so I just draw the profile of the workpiece, right? So definitely there will be some phase shift. Okay, so here, okay, this is the axis of the rotation. So here actually you have the thickness you want to, the chip thickness that you want to be removed away. Let's say it's intended thickness H0. Don't know if you can see clear. Okay. This H0 is let's say it's ideal condition. You want to manufacture this workpiece. Every time when the workpiece rotate the rotation, you want to remove H mean thickness of the chip. And here you will have, let's say this is 2 times, right? When you manufacture here, this curve, and second time when this coming back will be removed until this surface. So here we say this, let's say this is the actual chip thickness. It means it's the real removed thickness on the workpiece. So there will be difference between H0 and HD, of course, right? And we can calculate here. Let's say the distance from here is displacement in the axis direction, as we mentioned in the last lecture. Because you're doing this kind of some mass dumping system, you have applied a force, and also you have to define the displacement caused by this force, y, t, or ft. right? So this is the same. So here you have, we will say this is yt minus t, and this t is the time period for one spindle revolution. So, and here we define it as yt. So this is the current distance. So from here, from this figure, actually I think you can very easy work out ht equal h0. First we plus yt minus t, and then we minus this one yt, right? So this part is, so you got this part plus this part minus this part, right? So this is actually the actual chip thickness, and this is the intended chip thickness. Okay, so let's do some here, and then you have, okay, yt minus yt. Okay, so this is actually the equation of the intended thickness H-nin and the relationship between the actual chip thickness. If you see this model, 1 degree freedom model. So let's move to the next slide. So we are going to do a scientific modeling of this system and see what causes this kind of shadow vibration. So here we are assuming this, as I told before. Here we assuming okay, maybe here it's all clear. We're assuming that this system is a 1 degree of freedom system, and because of this cutting force, will exceed the structural vibration of the CNC machines. So the dynamic chip thickness HT, as we mentioned, will be varying, changing due to this kind of cutting force applied on this workpiece in the radical direction, because we assume it is a 1 degree of freedom. And then we lend this cutting force FT. So it's very easy to obtain this equation, because last time you already have experienced how to model in this kind of two old dynamic system. Actually, they are mass and their coefficients for the spring Ky and the coefficients for the damping Cy. And all these kind of things you plug together is equal to the cutting force in the radical direction FF. But FF can also express as KFAH as shown here. And this K actually is a parameter that relates to the material of the workpiece. Let's say you have cut a very stiff, hard workpiece, you need more force. If you cut a kind of soft material, you don't need so much cutting force on it. Actually, A is just a parameter we show here already, the dimension of the cutting force. And the H, as we have already modeled here, is the actual chip thickness. So if you replace this actual thickness here, you obtain this equation. So this equation actually is very interesting. Like if you see clear, if you have y minus yt is bigger than h0, like means here in this equation is bigger than h0, then this h, let's say theoretically, is a negative value. But this is not realistic in in the real. Or why? Because you cannot be a negative value because you're cutting the workpiece. So this means the current will actually jumps out of the current producing, and there will be zero chip thickness. HT will be zero, and there will be zero cutting force. So this is kind of condition we worked out from this equation. Okay, here just show you a block diagram. Maybe it's better to show here so everybody can see. So here we already have this equation of the actual thickness. We have just write on this paper. So if we do the Laplace transforming, and then you will have the dynamic chip thickness in the frequency domain that it shows in this equation, right? So, and also we already in the last slide we say the cutting force can be equal to KFAH. It's a function of the actual chip thickness, and these parameters depends on what kind of material you want to cut. And so we can actually deduce the transform function between the let's say here is output. Output, if you remember, is the displacement in the axial direction. This is 1 degree freedom, right? And the F is cutting force. So this is the input and this is output. And this can be modeled as two-order system, dynamic system here. Actually, this is the equation of this one, right? We write in this way. And for general cases, we can write this equation like this with a transformation function of the machine structure here. This is the open loop system. You don't have, if you learn the control theory, you know this is an open loop system. It's just the physical characteristic of the machine, CNC machines. Let's say it is a 1 degree freedom mass dumping system. Or you can do it as a 2 degrees of freedom mass dumping system, or more complex one, right? Therefore, you can deduce the output here. We say this is the block diagram. You have the input is a reference chip thickness. This is what you want the machine to cut, the thickness every time. And this is the output of the vibration. Actually, it's the displacement in the axis or direction. And this is the structure transformation function of the machine structure. And this is the input. We can deduce this function. And you can see what kind of things can influence this vibration. First is the material you want to cut, KF, and the machine dimension of the machine tools, the actual chip thickness, and also the physical dynamic characteristics of the CNC machine. Okay. So here, if we come back to this block diagram later, here actually there are 2 loops here. This is inner modulation, actually with respect to the this kind of profile, right? And here the out is modulation, out modulation, actually related to the out profile, very wide-sided workspace surface, right? So here is just if you later we will show you the transformer function as the input of H0 and output of Y, because here we just deduce the transfer function for the machine structure, right? So here we show you the characteristic equation for this charted vibration dynamics. So the transformation function between the dynamic and the reference chip thickness, because you remember I just show you in this piece we work out the equation between the reference chip thickness and the actual chip thickness. It's a function of the vibration between one rotate of the spindle. And here it shows, okay, so here is the output of the actual chip thickness, and this is the reference chip thickness. And this equation actually we already, you can deduce from here, right? You just write this equation this way. So this is actually a one old system. It's a time delay system. If you learn this control theory, right? We call it this kind of is a too old system, dynamic system. It's one older dynamic system. So the stability of the closed loop transformation function actually is determined by the root of these characteristic equations related to CE. And so this part should be 0 if we want to be this system stable. Stable means you don't want the Y, the vibration caused by the cutting force to become bigger and bigger and bigger. You want to keep it to a certain value or reduce it to obtain a very good manufacturing quality surface. Okay, so let's say if we assume this one 0, we are assuming the root of this equation. You want to solve this equation, right? Because this one is, you can write as real part plus imaginary part, epsilon g omega c. Actually, this omega c is the we name it chattering frequency. I will show you later. Right? So from this, if you assuming this root, that if this is positive, if we do this in a time domain analysis, the solution you will get is with a very positive power, like this cutting force. When you apply to the workpiece, it self-regeneration some positive power, and this positive power will cause larger displacement of the, as we showed, the mass, the machining tool, not machining tool, but this kind of workpiece. There will be a larger vibration, and this will introduce unstable vibration chatter. Okay. So if epsilon is a -1, this is a negative power, like every time you reduce this vibration. And this will introduce this kind of stable vibration. So this is just a very rough analysis. Then the conclusion, the question is coming, how can we calculate which kind of frequency of the chart you want to avoid, right? Because this charting frequency is caused by several reasons. The material, actually main reason you can control is the rotation velocity of your spindle of your CNC machine. You slow down or accelerate it, will reduce this kind of chart vibration. Okay. So here we count the very critical, we call it critical stability for this equation. as we said here, we just say this rod is negative or positive, but there's some condition. This one, let's assume it's 0. And then you substitute this rod, because you assume this is 0, of course, right? It's in 0. The real part of this value. And in this equation, if you substitute S equal G omega C, you get this equation to be 0, right? And here this A lim is the maximum actual depth cut for the chatter-free machine. This is a kind of condition you can prevent the chattering vibration happens. So if you want to be this equation 0, actually this transformation, we assuming the transformation function of the machining can be divided into 2 parts, the real and the imaginary parts. For example, do you remember this is the TF of the machine structure? It's the open loop. It's a physical characteristic of the dynamics of the machine, CNC machine structure, right? So here you do like this, the real part and the imaginary part of this transform function of the machine. Just 1 degrees of freedom dynamic system. Right? Actually, you substitute the TF into this equation, and you do some transforming, and you rewrite this equation into this kind of format in 2 parts. This is the real parts, and this is the imaginary parts. Right? As you can see, there's a G here, right? And then we will, based on this equation, we will analysis and get some key parameters about the chattering vibration. So here, both, because we are assuming in this condition, you want the S to be 0 or epsilon to be 0. Then these 2 parts should be also 0, right? Both the real and imaginary parts of the C must be 0. So if we first we see the imaginary parts of the critical equation. So it's this part. So if you want this part to be 0, and then this part, if it is 0, and then whole equation will be 0. So here you deduce this function, assuming it to be 0, and then you do some transforming, and you get, actually here is right the TF of the machine, right? 1 degrees freedom dynamic system, a mass spring damping system. You write in this way, and this is a function actually of the, as you can see, is a function of the omega c. We say the chattering frequency, and the actual t, if you remember, is the time when the spindle rotates 1 time, right? Here you have you machined from y/t minus t. This is the t time before, and you up this t time, your tool comes to this surface. So actually this t is related to the time of the rotation, spindle rotation time. It's kind of velocity. Okay. So here we are doing the analysis, and you can write. This is just some mathematical you already learned in your mathematical lessons. You can check later, right? Or you can read the, if you want to know more details, you can check the textbook. I don't know if everybody have the PDF file or handbook of the textbook. No. I will upload several pages of this on our NTU learning, so you can really know how can you deduce this function. Of course, in the exam, I will not ask you to do this, right? And you can write this equation like this, because in this lesson just give you introduction how you can find the method or to real analysis this kind of physical phenomena in a scientific way, right? And then because you don't need to remember all this in your head, now you can Google or find the textbook when you really do a machine design or analysis. Here we get the equation like omega c. We say this chattering vibration frequency. The time of the a function of the spindle revolution speed, and equals 3 pi plus 2 epsilon. Okay, so this equation actually you can deduce it as attaching this h divided by g. This is we call it the phase difference of the CNC machine structure. Okay, so of course you have this kind of number of waves on the workpiece surface, and we actually FC is related to W omega c. It's just the relation of O to pi. You rewrite this equation like this, and we name this K is the integral number of waves, and this is actually a slight difference between these, right? If you see here, right, the difference between this point and this point. This is the phase difference. As we mentioned before, if there is the phase difference is 0, and then the vibration of the charge vibration will not increase expanding, right? They will keep stable, right? But in real situation, this time these things will happen, right? This is the phase difference between the inner and outer modulation. We name it this kind of modulation, inner one, outer modulation. Right. So here comes the spindle speed. If the spindle speed with the natural frequency for vibration, phase is 0, and then the machine is stable. Of course, there will still be this kind of displacement, the unevenness of the machine surface, because this is caused by the machining cutting force. This is the first vibration reason we mentioned here, right? This cannot prevent, because this is because of the machine is it's a dynamic system, or because of the tool or problem, or mass imbalance of the workpiece or the machining tool. Here, but there is no, this one is stable, this kind of regenerated charge vibration in this situation. If the phase angle is 0. And then we can also deduce the angle value of this one. I will show you later. And remember, we want this equation to be 0, and we divide this to be a real part and the imaginary part. Just then we just considering about this part to be 0, and then we deduce the relationship of the chattering vibration frequency in terms of the spindle revolution velocity and the phase difference. These critical parameters related to the vibration is stable or not stable. And in order to prevent this vibration, you still need to be in this critical equation, you still want the real part to be 0. So here we come to the real part of this critical equation. That is this one, and then you can calculation the maximum, let's say A is the maximum axial depth. You know the axial depth is the feeding alongside the feeding direction of the machine tool, right? It's actually it's Y, right? For the chart-free machining. So this is a critical value. So we obtained how to calculate this value, and you substitute in this equation. Actually here, this -1 is here, right? Okay, because here is. I will correct this and upload again the sliders. Okay, yeah, this is just the TF of the machine. Yeah, and if you rearrange this equation, it's a kind of mathematical deduction. You can write this in this way. So this value is quite important and interesting. That it means this depth of cut can only have a valid solution for the negative value of G. What it means? If you do this frequency analysis of a transform function of a kind of this kind of 1 degree freedom, you will find out in some frequency domain this system is stable, but in some frequency domain this one is not stable, especially in the 2 degrees of freedom system. If you have basic knowledge of the control theory. So here it means you have to select the frequency in the negative value of this G omega C, right? To transfer the TF of the machine system. Oh, it's not the machine system. This is part of the it's a part of the let's see, it's a part of this the imaginary part, real part of the TF of the dynamic characteristic of the machines, right? So here we come to the conclusion again. Actually, if you have a depth of cut, it's bigger than a limb, the maximum allowed value. Let's say you want the machine to cut a lot, and then will be chart happens. And if you regulate the feeding speed or the intended cutting a cheaper thickness in the region, in this maximum value, there will be no chart happening because this limb is, if you think about it, it's very intuitive. This alpha limb, this, let's take example, the hard material, let's say very hard material, you of course will reduce a very small value of the regulated value. Let's say you cannot cut a lot if you are cutting a very hard material, right? And if you have a very bad system, like the machine when you're doing machining is shaking, not rigid, you have some problem of some components installed on the machine. This means you have this kind of value is not so rigid. There will be a lot of vibration here, So if you going to see the real machine, they have a very heavy base in order to keep this value lower when you do machining. Because when you do machining, of course, you will build vibration. But if you have a very rigid body, and you have a very good without eddy clearance, reduce this kind of damping or spring value, you can get a real good stiffness. And then if you have a bad machine, of course, this value will be quite small, and then you cannot cut too much. Otherwise, this will introduce a chatter vibration. Okay, so if you have a very low value of this alim, the chart works more easy. So this is actually the kind of designer principle guidelines for this kind of machining, CNC machining manufacturers. Like they want the machine to be stable. They want the machine, the no vibration between the workpiece and the machine itself. In order to increase this alim, that means it's very in the customer's point of view is good, because you can cut your materials in a more productive way, right? Let's say if you have a very big alim, then you can cut more than a small value of this machine. So the speed can be increased. Let's say you can produce 100. Before that, you can produce only 90 pieces of components in an hour. Now you increase this value, now you can produce 100. So this is really, in the chartering analysis point of view, is a very critical value. So the manufacturers they're doing tests in order to increase this value, right? So they are actually, we are using a computer or this kind of algorithms to calculate what's the frequency for, let's say you have a machine, you want to know what's the chattering vibration frequency, so you can regulate the spin velocity in order to prevent it. Say you are an engineer, now you want to manufacture a workpiece, then you did the calculations, and you said you cannot set the spindle velocity in 2000 revolution per minute, because that will cause the chattering vibration. So this, to understand the natural frequency and also the chatter vibration frequency is quite critical for the manufacturing, also for the user or engineers, if you have some this kind of ideas. So there's an algorithm here. Actually, they are, of course, they are software. It's very convenient to use. They already have this algorithm in it. You just need to prescribe several parameters. You can get do some experiment. You can get the chattering frequency. Here, let's explain a little bit about this algorithm. You first you select a chatter frequency, omega c. This is the chatter frequency. It is the negative real part of this transfer function. We just explained here, right? Make this system stable. Then you calculate the phase angle of structure. The phase angle here. If 0, then it's okay, right? It cannot be 0 always. Then you calculate the critical depths of cut. This one, right? Also, this parameter is critical, and this one is also critical. This one 0 means there is this chatter vibration, but it doesn't increase. It's okay, right? This one can prevent chatter. And then you can calculate the spindle speed from the equation for each stability load, like for different frequency domain here, because you select, right? And then you can you already get these equations, these values, two important values, and then you repeat these steps by scanning the chatter frequency around the natural frequency of the structure. What does that mean? Because we have a natural frequency of the structure, means the machine, this transformation of the machine physical dynamic structure has its own frequency. As we said, if you harmonic this frequency with the machine frequency, it will cause this kind of vibration, right? So the chatter vibration frequency actually is nearby the natural frequency of the structure, but it's not the same. If you see it clear, right? Here is the chattering vibration frequency. And here is related to actually the machine structure. Yeah. Okay, so I think this is really an algorithm that you can you can select from experiment test. You can get the natural frequency of the machine, right? You use a hammer with different frequency. You have touch the accelerometer sensor on the machine, and then you will get the data from the accelerometer. You do some frequency analysis. You know what's the value of the natural frequency of the machine structure. Normally for this kind of big machine, there will be no higher natural frequency, but it depends on the machine structure. And from this, you already know this, and you select this. You assume it a chatter frequency nearby, and then you can calculate the critical value, like phase difference angle and this critical depth cut, right? So you make a table, and this table can be very helpful for your user, so or for your manufacturing program, because now everything is already programmed. This kind of software engineer in these companies, they know in what kind of workpiece is good for what kind of spindle velocity, right? Let's say you select this kind of steel, they already calculate for you in this velocity there will be no chatter, and all these things you have a table. They already have this knowledge based in the CNC machine software. Then the use don't need to consider about the charting. Every time they cutting different materials, no chart happen. You cut wood or steel or very hard machines. If you cut very hard materials, of course the spindle velocity will reduce, right? Because every time you remove it a bit. But also they can optimize. Like even for different machines, there will be different productivity. Some good machines they can cut the workpiece in 10 minutes. Other old machine need to manufacture in 1 hour. So that is the magic between like let's say a German made CNC machine and or China made CNC machine, right? So this is really the technology of this experiment taste behind of this high quality products. They already did tens of experiment results. They already did optimization of the mechanical parts and the software parts. So comes to a very good machine. I think we take a break, right? There are a lot of equations you get puzzled, right? Okay, good. Let's take a break. I think Prof. Tegu already sent you some assignments. If you finish, you can hand over to me, right? If you didn't finish, you can hand the next time. Still have 2 lessons to come, right? Okay. Yes.
I have a question to this.
Okay. So for the guys who didn't take break, I'd like to show you this laser, this kind of state-of-art technology in this CNC machine manufacturers. Actually, it's very, I know this one. It's very impressive. In the multimedia, right? You should see this. It's really impressive. It's just all these kind of things. That is using a plastic material, but this one is really using a material, using laser to do this kind of additive manufacturing. What's important is they combine these 2 kind of machine together. So I think everybody already here, right? Let's conclude this half an hour. Everybody will be happy to go back home earlier, right? Actually, just in the break, I can show you the video I mentioned before, the BNG Mori state-of-art technology. Somebody didn't see. I want to play this again. I don't know if it's this one or it's a different one. Right? Okay, just see this laser tech. Huh? Okay, it is this one. It is. I really see this machine in the factory of BMG Mori in Singapore in twice. Actually, it's quite nearby. And this is really amazing. If you look at this, combine this 3D printer with a CNC machine seamlessly. So this kind of 3D printer is just a tool, like a cutting tool. But this tool is a laser additive tool, as you can see the red one. So it really can using this laser to print this kind of steel or other material, layer by layer. So actually here, in this kind of way, if you want to manufacture this one, it's not an easy task, and it wastes a lot of materials, right? Because this one inside is hollowness, and you take a lot of time and waste a lot of materials. But with this technology, they can really build this very complex component. Actually, this is a component for the ARA plane, right? They just change the tool, right? So like 3D printer, you print this kind of material powders, and after that, you change the milling tool or cutting tool to do a perfect milling, right? For this kind of critical component, you can replace this broken component in a very short time. Right, after this, you do mining in the same machine. We're going to, I think MA is going to buy this machine, Professor Tsai, I think. They have a strategy collaboration with DNG Mori. If you have chance, you definitely go to take a look. Okay. Okay, so we come back to the lecture. So, okay, here is because Professor Tagore come back to after he introduced 1 degrees of freedom system, he also introduced the 2 degrees of freedom mass spring damping system. The other one is more complex than the 1 single degrees of freedom system. Why? Because it integrate together all this kind of phenomena. It's a little bit complex. So here actually is, this picture shows a kind of a milling process. The last 1 single degrees freedom system we modeled as a cutting system in orthogonal axis kind of cutting. This kind of mining, I don't know if you're familiar with it. I'll just show you a video, right? This is the most intuitive way to understand. So, so here is the video shows CNC milling machine. Actually, it's a 2 degrees freedom system. if you say it works in a plane, the two-degree freedom system, it moves in a plane. But also it has data access movement capability. So it's doing some polishing. So it has 2 degrees of freedom, like change the tool. You do the meaning. Right? So you can move in a plane with 2 degrees of freedom. Okay. So this kind of 2 degrees freedom we can model in this way. That you have this machine tool, the Mars object with 2 dynamic system, 2 parts. Also simplify this spring or damping. There will be cutting force in normal to the workpiece. Also, there is cutting force parallel to the workpiece, and this is very similar. But there's some difference. So if we look from the top to down, you can have this kind of system, right? You can move to x-axis or y-axis. So it's 2 degrees freedom. Also 1 degrees freedom. Each one is a kind of mass damping system, but they're coupling together to make this modeling more complex than a single degrees freedom dynamic system. So here you have the workpiece. Of course, here the dynamic chip thickness is a little bit different because you are not dealing with only one axis. You are dealing with 2 axes, x and y. So we are modeling in this way is that you add angle as a parameter, right? Because the other one we just considering y is displacement caused by the machining force on the tool. And here we have 2 parameters, and then the dynamic chip thickness. Actually, you can see from these 3 figures. The first figure shows the static chip thickness. It's what you what we want is HT, right? And then you should minus the vibration at the present tooth period. It's just like we mentioned. It's mining. After mining 1 turn of mining, you come to this. This is the previous tool period, right? The first mining on this surface after one revolution, you're doing another layer of this meaning, right? So there's a difference of this T also over there. So actually, you can call it the dynamic chip thickness or the actual chip thickness. It can be replaced by represented by this equation. So let's take a look. What is the difference for the 1 degrees freedom system? Because the other one is just the H0 minus YT minus YT minus this big T, right? It's just a function of the reference, the chip thickness and the vibration caused by the cutting tool. So this G function is a function of this. Actually it's the unit step function. Just determine whether cutting tooth is in or out of the cut. It is either 1 or either 0. So either 1, if the value is 1, it means this tool is inside the start and exit the initial angle of the cut. And if the 0 is out, it means right. So this is just the unit step function. But let's take a look of this equation we write in this way, right? The static components. These components we can be negative because it does not contribute to the dynamic chip load generation mechanisms. Why you can look into the textbook details. Here we just explain this part. Actually, this H can be deduced as, let's say, if you have, I don't know if you understand here, just better here. You have the angle here, right? So if it's probably then okay, so you have this kind of 2 degrees of freedom system. X-axis and y-axis. Here you have another parameter, is angle, right? Expect the time. So actually the vibration in x-axis, right? Here. Oh, let's do like this. Should be do like this. Because you contribute to the displacement in this direction, right? The current tool moves to this direction. If you see this figure, right? This is the displacement we want it. It's a dynamic the chip thickness, right? So let's see how this displacement in x-axis, this one, and y-axis contribute to this one, right? So if you do this, let's say here you data y. If then you data y, you do the cosine theta. You contribute to the displacement of this in this axis. So it's what's the I don't know if I explain it clear, right? And the same reason for you have for x-axis, right? So it should be like this. So if this one is theta, then it should be this one theta. Then if you contribute here, that x should be sine that x. Its distance should be that x sine. So this is the equation we obtained that in x-axis and y-axis contribute to the displacement along the cutting tool axial axis. Right, this is just a unit function. Okay, so it's the same. You need to think about the relationship between the cutting force and the displacement, let's say the vibration distance of this kind of dynamic system in 2 axes. And in last lecture, Professor Tagore already did using a matrix, so it's more compact. You see, you can write into equations, but this kind of matrix looks like more slim and meaningful, right? So we are represented in the matrix form. So this you can see the cutting force of along the x-axis and the y-axis is a function of the displacement in x, not only x and y. So it's accompanying together this kind of force, right? So in these matrices, they're accompanying together. to make this is a little bit more complex than single degrees of freedom system, right? So the details here you can it is the equation for this kind of 2 degrees of freedom system. But I remember Professor Tagu is just told you they are in a serial chain, right? You have two mass connected in a serial chain structure, like 2 mass, 3 springs, right? But this one is only 1 mass and 2 spring damping system. Right? So the equation could be different, but it's easy to deduce. Okay, so this is a fundamental difference between the mining and the turning operation, because in turning the force direction is along the feed direction of your tool is constant, but this one the force will change, right, because of the displacement different in x and y axis. Okay, so also we need to consider about the stability of this kind of chattering vibration for this meaning process. And we're considering in zero order solution, because for high frequencies can be more complex, right? So here I will not give you more details, because these kind of equations it's a little bit hard to understand in a very short period of time. But don't worry, I will not keep examples this part, to all the system. You don't need to worry about. Just have a general idea how it works. And if last time you encounter this kind of problem, you just repeat the textbook and do as the following. And it's just some deduction of this kind of metric curves, the force metric curves, and you get the dynamic minimum force in a very compact way, related to the also you will see this kind of material related factors, and also the displacement in x or y axis. Right, here is the matrix. Okay, so actually this kind of machine structure natural frequency, we always do experiment test. Why? The reason is you cannot modeling this kind of machine in you can, but it's very difficult to get the parameters, like what's the value of the spring, what's the value of the damping, how heavy it is. How heavy it is you can calculation, but always is not so precisely. Nevertheless, say this machine cannot modeling as a single degrees of freedom. It's a multi-degrees of freedom, calculating the different frequency characteristics. So always in a practical way, in engineering, they always do experiment test. In a numerical way, they obtain the natural frequency of the machine structure. Like this figure shows, you can use an impact hammer, and you have several accelerometers attached to the spindle of the machine, and you receive this kind of sensing information of amplifier, and then you record this value in your computer. So you repeat this kind of tester. Of course, you can use a mechanical device to automatically this procedure. And here shows some test result, and you can see. I think this natural frequency is mainly it's like 600 hertz for this test. This is just example, right? And here the equation shows this kind of 2 degrees of freedom dynamic system. They are the TF, the transform function, is also coming together, right? They are transfer functions in x and y directions also cross the transfer functions, which is coupling together. Okay. So here is I know you guys will be get shocked of this kind of complex drawing. Just take from the textbook. If you're interested, you can look into more details. Actually, this is the broad run as we did for the 1 single degrees freedom. You remember that one? It's input and output relationship. Input is reference chip thickness you want. The output is the vibration of the along the feeding direction, or we say the axial direction. Here is the same, but because this system is complex, we expressed it in matrix form. So here, if you start from here, then you can see the dynamic cutting force in different frequency domain, right? To write it like this is a vector, and you have the transfer function, right? This is the machine structure transfer function, and you have this kind of present dynamic displacement minus this previous dynamic displacement, and output the regenerative displacement in x and y axis. This is the same of that for the 1 degrees of freedom system, and you have this kind of force coefficients and the depth of cut in different. If you do in a time domain or frequency domain. In general, we do it in time domain, so in a numerical way. Also, we have the critical equation, like we mentioned for the 1 degrees of freedom system. And this equation, this is displacement in x and y axis. This is the previous dynamic displacement in x and y axis. All these are vectors, right? So here, if you see this, it's very similar, right? And then you're describing the vibration as a vibration frequency in the frequency domain. It's a kind of Laplace transformation, right? You will get this kind of. Do you remember we do the Laplace transform for ht? That is h0 minus. Don't remember exactly, but it is the same thing. You have this, right? You substitute the expression for dynamic mining process, and you get this. And then you remember for critical equation, we want to be 0. Here is the matrix should be 0. So you have this also this transform function of the 2 degrees freedom dynamic system, and you need to calculate the aging-value of this critical equation. As last time, Stego already explained how to calculate the aging-value of this critical equation. It's a similar procedure. You compute the critical value for one single degrees freedom, but this is matrix related. It's a kind of algebraic math, and the result becomes this should be 0, and then you can find this kind of value, right? So here we comes again the limit depths of the card for the chart-free mining operation. So this is not a one value, it's a vector in x and y directions because you have the matrix, right? And also the corresponding spindle speed that is similar to the I have presented for the chart in the single degree freedom orthogonal cutting, right? So I will not propose more details about this. So, but if you like, you can read the textbook instead. But here they can calculate this kind of spindle speed, the function of time. So also there are algorithms. Sorry. You can select the charting frequency also in a domain model, which is nearby the natural frequency of the machine itself. You need to solve the eigenvalue, that is kind of critical parameters, as we did like phase difference angle or the maximum depth of cut, right? And then you can make a map the same for this kind of machine. So it's a different method. Just you need more advanced mathematical tool to deal with it. And you can also, this can be very helpful for the design firstly or programming the machine to get a better performance. Okay, so here is actually there's some result. So in the experimental results to show this kind of stability of the chart vibration. Here the x-axis is the spindle speed revolution of your chuck spindle, and here is the vibration. It's the axial depth of cut, right? So of course you increase spindle revolution velocity in certain period of time you cut more, right? So you select a kind of spindle speeder, and you can get this kind of feeding force in the time domain. And if you do the fast Fourier transformation to do the frequency analysis in frequency domain, you can find that there will not any much frequency cause charting vibration, right? So this is kind of a stable condition. And here this figure shows this kind of unstable condition, right? And you can see actually the cutting force in x-axis is vibration a lot, right? Yeah, here you have a very good light cutting force. It's regulated in this value, but this one is much bigger, and there are a lot of higher frequency domain, especially in this frequency, right? So it's like you need to prevent that machine works in this frequency, because this will cause chattering vibration for this kind of system. Okay, I think we come to the conclusion, and then next lecture I will give you a presentation about the CNC machine, how it works, and what's the structure, and how you can programming the CNC machine using G-code. That one is very important. If you're engineers, you definitely need to know how to program a robot or CNC machine using G code, the basic knowledge, right? Because if you do mechanical or even learn robot, because there are now somebody using robot to do CNC machines. Okay, thanks. Have a good weekend. Okay.